Sorry to start a bit late, but let's start. Lecture 4, and what I hope to do today is first talk about some simple models of quantum chaos. I mean, the billiards problem is complicated enough, although it looks simple. It's a single particle moving around, but to solve the Schrodinger equation with those particular boundary conditions is a non-trivial numerical ask. So, and also to analyze it analytically or to progress further numerically, it's harder. So much simpler models, such as what we studied in the classical case, we can study corresponding quantum things. So simple models of quantum chaos, especially quantum maps. So just as classical maps, the quantization of these. I'll just mention a few canonical maps and what are the kind of physics that comes out of that. So simple models of quantum chaos, and they're not often just models. There are experiments and realizations of these things. Then I'll start with energy eigenvalues. We yesterday talked and showed about eigenfunctions. So we'll talk about the spectrum, energy eigenvalues, and show how they behave. So integrable versus non-integral. This should motivate a study of random matrices, so I hope to start a bit and give an overview of random matrices, especially the eigenvalue part today. Maybe talk about eigenvectors tomorrow, but I'll give what I hope would be a practical introduction. It's a vast subject with. But I would just say some things which I would not prove a whole lot of things. Okay, so simple models of quantum chaos. Let's go back to classical chaos. And let's look at the simplest thing where chaos is possible, 1.5 degrees of freedom. So Hamiltonian systems with 1 degree of freedom, time dependence. And we'll also have the simplest kind of time dependence. So we saw the Jekyll and Hyde Hamiltonian, where you had a time dependence which was on and off, or changing signs, flipping, so like a square wave. But as I said, a simpler thing to consider would be a class of, so that's 1 degree of freedom, no chaos, but we now introduce the time dependence via these periodic perturbations or periodic kicks at time period t. So it's a train of kicks from minus infinity to infinity, train of delta functions or a delta comb. That's this time dependence. And we derived, therefore, recall that this is a time axis. So at some time n times the time period and n plus 1 times the time period, these are these two. And we monitor what happens to the phase space variables just after the nth kick and just after the n plus 1th kick. That provides a stroboscopic map, as we discussed in lecture 1. And they are given by Qn plus 1, Qn plus Pn time between the kicks. Pn plus 1 is Pn minus t, the derivative of the potential, that's a force, that's the impulse, at time n plus 1. So this gives you an area preserving mapping of the plane onto itself for any function v. And this is the time t between the kicks. You can see that as t goes towards 0, if we were to rearrange this and just write it like this, then this looks like Euler discretization of a differential equation. as t goes to 0, and remember that this is the position at time nt plus t, so these things differ by a time t, capital T, and therefore the limit t going to 0, these things simply become dq by dt is p, dp by dt is negative vq. That's the familiar Newton's laws or Hamilton's laws for 1 degree of freedom systems. So as t tends towards 0, we know that it goes towards a regular dynamics, which is that, but all the fun and games is when t is large, and then it can go into chaos. Right? So that's the class of maps which we saw, like in particular the standard map. Was a kick pendulum, call that G, cosine potential, just Q. So that's a nonlinear potential, and the resulting classical map is the standard map. We showed some pictures of it on the first day, and it has a transition. So if we write out the standard map, and this in a rescaled coordinates, they are this. Where this k is related to this constant here and the time between the kicks. So the time between the kicks has disappeared from here by rescaling the momentum t times pn as the new momentum. Okay? So that's why this t has disappeared. And there is only one parameter, therefore, in this in the classical standard map, namely this parameter k. And if k is large enough, this leads to chaos, as we saw. And this q is an angle because it's cos q and it's periodic. So let's put modulo 1 on this. And the phase space of this is naturally a cylinder. So you should think of a pendulum that is being periodically kicked, and its angular momentum can increase or decrease. And so that's the angular momentum direction, and that's the angle theta direction, or q direction. Okay. Now, a classical consequence, before we quantize this, a classical consequence of this thing, maybe I just take this up for a minute. It's diffusion. Diffusion in momentum. For large k, let's say k greater than 5, but let me just write k much greater than 5, so that all the regular, it's far from an integrable case, and it's gone into a chaotic phase. Then diffusion is observed in momentum. Namely, if you do the following experiment, if you take in the phase space, so this is, I'm just unfolding the cylinder, so that this is 0, 1, that's q, and that's p. Let's take all momentum 0, initial momentum 0. You take a bunch of points, initial points, spread them around the circle. Okay? So all of these are just free particles, or they're just particles uniformly distributed on the circle. And they're stationary to begin with. And then you start this process of kicking it, and its momentum will increase. Some of the momentum will increase, decrease. So the question is, what happens to the average momentum? What happens to the average momentum squared? The energy of this particle. So you can estimate, I'm just going to very quickly estimate this. It's just so let's look at P1. P1 is P0, that's at time 0. This is at time 1, k by 2 pi sine 2 pi Q1. So P1 minus P0, just a rearrangement of that. And similarly, P2 minus P1, k by 2 pi sine 2 pi q2. And if you add them together, it just telescopes. You get a cancellation of this P1 and minus P1. You get P2 minus P0, the momentum at time 0, minus the momentum at time 2 minus 0 is k by 2 pi, sum of these two. So of course, the momentum at time n similarly, minus momentum at time 0, minus k by 2 pi, and you have a sum sine 2 pi qj, j1 to n. Okay, so that's exact. There's no approximations made at till this point. The approximations get made here if suppose you were to just look at the average of this quantity. And what do we mean by average? Average over this initial ensemble. Now we don't have just one trajectory. We have many different trajectories doing many different things. Just starting off from that. So that's the average that we're going to do. Average of P0 is, anyway P0 is 0. We can probably put for all of them 0. So let's just set, because for this entire ensemble we are starting from P0 is 0. So average value of Pn, average of sine 2 pi qj. Now if we invoke a ergodicity and say that this q, it's chaotic enough that this q is going around all over the circle and covers it uniformly, then this average of these, each of these is 0, and actually the average momentum is 0 over the ensemble. So the average square is some k squared by 4 pi squared, and sum of the squares of these, so let me first write this, plus a sum of I not equal to j sine 2 pi q I sine 2 pi q j. Okay? And then we need to take an average of these. Now if we argue, and it's really an argument that needs justification, but if we argue that these sine 2 pi q are now like random faces, and they are not correlated, this is only an approximation, but suppose we throw away all of these things when q is, when I is not equal to j, we say that the average vanishes, then we have only this left, and this average is 1/2, again invoking ergodicity and replacing this by an integral. So we have, this is just contributing 1/2, but there's a sum over j from 1 to n that gives you this n. And you see that the average kinetic energy, or the average momentum square, is growing linearly in time. That looks exactly like a normal diffusive walker. And in fact, if you do numerical experiments, you will see this diffusion. It's actually part of an exercise from chapter 1. Yeah. The ensemble, the initial ensemble in Q. Yeah, the Qs are spread out. Yeah, so that's why we can just do this. Yeah, so, yeah. So actually, it's an interesting phenomenon. Classically, there exists also anomalous transport in this in the presence of some accelerator modes and so on. But for us, it's for most of the values of k, which is large, you will observe normal diffusive transport in this behavior. The fact that we have neglected these can be taken into account systematically. The most important correlations would come from actually those that are separated by one time step. So 2 pi qi sine 2 pi qi plus 1. Actually, this vanishes, exactly vanishes, So the one that really contributes is Qi plus 2. Then it leads to Bessel function oscillations, which are also observable numerically. But the principal thing, I mean, that doesn't change the fact that it's a normal diffusion. It only changes the diffusion constant. So there are some oscillations in the diffusion. I mean, there's k squared, but there's also some oscillatory corrections on that. Okay, so this is a case where initially, when k is small, there is these regular tori and regular structures which are blocking transport. And as you're increasing k, there's some critical parameter after which you have transport that tends to become normal. In fact, this was studied. This was of interest in plasma physics when you are forcing some, you're forcing charged particles and you want to see how much of energy is being absorbed by them. So the early studies with all of these was done by plasma physicists. So if you go back now we are, as I said, quantum, if we can ask what happens to this diffusion if you were to quantize the system. And the quantization of that system is quite straightforward because we have a Hamiltonian and it's just 1.5 degrees of freedom except that it's kicked. So now suppose, what is a quantum map? So the classical map connected states just after 2 kicks or separated by 2 kicks. Separated by a time which is the time period of the kick. So the quantum map is similarly something which, if there is a state of the system at time nt, it goes to the state at time n plus 1 into t, and it's quantum mechanics, so when it's a time evolution, it's connected by an unitary operator. This unitary operator is the corresponding quantum map. So that's just the propagator, time propagator of the system. So how do we propagate this? So it's a free motion from n plus 1 just after time n. This is time n plus 1. It's free just before the next kick. So that time evolution is given by e to the minus I. It's just free particles minus twice. I've taken mass to be 1 h bar time period t. Usual propagator in quantum mechanics. A free particle. But now, it's not free just in this neighborhood of time. Just in this epsilon neighborhood around time neighborhood of n plus 1, there is this kick, and during this kick, you may ignore the kinetic energy. You can do a more careful analysis, but let me just say that you can ignore the kinetic energy, and then what you have is just the potential energy, which is there, and it occurs. So when you integrate out the delta function, you will get a time t, which is sitting there, and you see in terms of units, everything must be consistent. I have defined the Hamiltonian to be such that the delta function is dimensionless, because there's already, I've divided t by t, so it's dimensionless. And therefore, V has the dimensions of energy, and you need to multiply that by t, but you also get that by just integrating the delta function. So that is the quantum map, that's all, it's as simple as that. That's the unitary operator that connects these two. So let's just pause to look at the structure of this. It's an exponential of an operator, which is Hermitian. So this is a unitary operator. It's a product of 2 unitary operators. And they don't commute. After all, momentum doesn't commute. So this is the structure of a lot of classical, Floquet kind of, non-trivial Floquet kind of system. If we take the limit as t goes to 0, what can you say as an approximation to this u? Huh? What approximation would you make? Yeah? Oh, you want to expand? Well, yes, you could, but I want to keep it as exponentials. What approximation would you make? You know that e to the power of a, yeah, exactly. You know that e to the power of a, e to the power of b is not equal to a plus b. And then there is, unless they commute, and then you have commutator corrections and so on. Huh? But if suppose there is a small factor tau which is multiplying that, it's this, and then there are corrections which are tau squared and maybe so on. So, yeah. So if we look at such an approximation, when tau is small, then this is approximately minus t by h bar I p squared by 2 plus v of q. What is this the time evolution operator of over a time t? It's the unkicked one, which is not chaotic, right? I mean, it's just 1 degree of freedom system. That's exactly the Euler, the classical thing of taking this and taking the limit as t goes to 0, and you get this 1 degree of freedom system. It's exactly the same thing. Sorry? No. That's the whole point. I mean, this is the... only if h is time independent. H is not time independent. You have to be careful when doing the integration. Yeah, you have to do a general thing here. Okay, so yeah, so this is not this is an approximation, and you see. So what I want to say is that this fact that e to the power a into e to the power b is not equal to that spells in this case a difference between chaos and no chaos. Okay, so if you make this approximation, you can go into a regime of no chaos. So you have to be, in this case, it's like Kepler, I mean, it's up to you. It's up to you, yeah. It's a parameter which you have. Okay, so now we can put, so these are operators now. It's a unitary operators, and nothing is known in general about it. For example, in 1 degree of freedom, a lot is known about that. If V is bounded, we know that you have a discrete spectrum. In this case, even if V is bounded, actually nothing is known in general about the spectrum of such things. Where is the spectrum? First of all, what do I mean by spectrum? So eigenvectors, let me say one important thing. Just as this does not depend on n itself. U does not depend on which way I'm integrating. That's clear, right? Where I'm integrating. Which kick I'm integrating at, it does not matter. If I integrate from here to here, I have the same operator. That's, in flow, when we discussed the classical stroboscopic, that's why we integrated over one time period and not some arbitrary time. So, so maybe before going to the spectrum, I would say that if you take some arbitrary initial state, phi at time 0, then acting on this once gives you the state after 1 kick. What do I have to do to find the state after 2 kicks? U squared and so on. So u to the power of n gives you the state after time n. Now I have dropped the capital T, but this is really n times capital T. No, there's no need for that. This is something which is independent of n. It's independent of this n. So you just have to take its powers. So it's come to something which is an autonomous system, but the autonomous thing is in the map. It's in the Floquet operator. The underlying system is still time dependent. Is that clear? Yes, so let me define eigenstates of this. So these are time evolving states, but this is a unitary operator. You can define a orthonormal basis for this, and I don't like to use this thing, but I'm going to use psi n here. Psi n's are wave functions, but so it's a unitary operator. These are orthonormal bunch of this n, let's say call it j. So it's a jth eigenstate, and the eigenvalues are modulos 1. So there is e to the I Psi j is an eigenvalue. Psi j is real. It lies in the interval 0 to pi. It's just an angle. So all of the eigenvalues are lying on this. They are winding. There are infinity of them. Does it form a continuous spectrum? Is it discrete? Is it some other thing like a Cantor set? Could be a fractal set. All of these things are observed in different kind of systems, but there are no general results. In fact, for the standard map, if you put cosine of Q there, it's a very important problem because it has implications of diffusion and so on. I believe it has been proved to be a discrete thing, but it's fairly recent. So anyway, so these things are, as the word was mentioned, quasi-energy. So they are real, and they play the role of energy in the usual time-independent things. Now, once you have this, let's look at what happens. Suppose V of Q is this cosine of Q. So in the case of the quantum standard map, so we have to write down the quantum standard map, but now the topology is the cylinder, so Q is actually an angle. It's not the plane. Q is an angle, and this is angular momentum. So you need to use angular momentum. Angular momentum is quantized at this because this is an angle. So if your coordinate is periodic, the corresponding conjugate momentum is discrete. And you know this is the usual angular momentum. So P is like the usual Jz, and you have M h bar quantization where M are integers. So momentum is discrete, position is, or the angle is continuous. So it's probably a good idea. We have to study this unitary operator, which means we have to write it in some basis. It's now too abstract. You want to put it on a computer, you need a matrix. So we want to express it in some basis, and the momentum basis is a good idea because it's discrete. So you might want to look at these where these are angular momentum, so like P. So let me call Q theta. Actually, it's 2 pi theta because I have modulo Q on that. So this is the angle operator, and this is the corresponding momentum operator, as you should know. Okay? Maybe there's 1 over 2 pi or something in that, h bars lurking around. But that's the thing. So if you were to calculate this matrix element, it's a matter of inserting complete states and so on and calculating some integrals. So let me write in terms of M prime. It's there in the notes. This is not very important. Okay, so that's the operator. There's an explicit recipe for a matrix element of this unitary operator. M is, yeah, plus minus 2 and so on. You can do, we want it in the momentum space, so you would do U, M prime. And here, M prime is no problem because it's already diagonal in that. So that's why you get this M square there. Here you will have to transform between position and momentum. So that's the usual Fourier transform, but now 1/2 of it is continuous, other half of it is discrete. 2 pi I Qm, just plane waves. Q to Q plus 1 is continuous. I mean, it's periodic. Sorry? Huh? There is no delta functions. Yeah. Yeah, that has been integrated away. So now you have only the propagator, which is connecting states between two periods. The delta function has been integrated away. We have taken that into account. That's why you got the V. There's no further mystery on this. Think about it. So this is the operator. So there are some observations. One observation is, how many parameters does this quantum map depend on? So first of all, I haven't defined tau. K is the same as that, so gt squared. Okay, so K is the same classical K. Tau is 4 pi square T. Sorry. K by tau h bar, tau h bar. So how many different parameters are there in this problem? There is K, and there is tau h bar. Tau h bar come together. That's the parameter. So actually the quantum one depends on two parameters, not one. And that's because of the appearance of h bar. And that has a very non-trivial role to play. So this one here is a Bessel function of order m prime minus m. And if this argument is much smaller than this order, then it is significant. Otherwise, it's going to die off. That means that for a given k by k by tau h bar, or given chaos, let's call this the chaos parameter or something like that. If you increase k, there's more classical chaos. So if this is not very large, this matrix is essentially a banded matrix. So if you were to look at it, how it is, so it's going to be banded matrix. This is just a face. Modulus is 1 throughout. But here this is going to lead to whether there's matrix elements or not. And the thing is that as this k is increasing, or this parameter is increasing, k by tau h bar is increasing, it gets more and more into a full matrix. Its bandwidth increases. Of course, nothing like a full matrix, it's actually an infinity by infinity matrix. So to do any numerical study of this, it's an infinity by infinity matrix, you need to truncate it with some number of momentum states, and it'll be approximately unitary at that case. This is exactly unitary by construction. You will have to truncate it, then ensure that whatever you're doing makes sense. If you were to propagate some initial state, you have to ensure that its normalization is preserved. Otherwise, you'll have to include other states. That means you're flowing out of that, the subspace is not large enough that you have chosen. Okay, so there are two parameters. And there's also a rather curious phenomenon here. What happens when tau h bar that appears here is 4 pi? You see, it comes in this phase, tau h bar. Tau is just related to the time between kicks. H bar is really up to us. That's effective Planck constant. So this tau h bar, if tau h bar is 4 pi, then these phases are all 1, because m is an integer. These phases are all 1, and they just completely disappear. And this is coming from the free motion. So it is as if there is only this potential part in this. This is something which does not happen classically. This is as if this is gone and this is only there. And this you can, I have indicated in the notes, you can do it as an exercise and see what happens now let's look at what we're going to calculate with it. Maybe after that I should tell you the story. So we could start with an initial state. Let's again do the classical experiment. We started with the momentum 0 state, and this is spread out everywhere. What is the corresponding quantum state? If I want to start with the corresponding quantum, I'll start with the momentum 0, m equal to 0 state. And you see m equal to 0 state is uniformly spread automatically in position. Anyway, all these states are modulus square is 1. It's independent of where you're starting on the position. Okay? So we can just start with state m equal to 0, raise it to the power of n, and we get the state, we get some state at time t. This is exactly like taking this ensemble. Now you don't need an ensemble, it's just one state. We propagate it with this map, and then you get this new state, and we have to measure the kinetic energy content in that. So the average of p squared. There's no further averaging, it's just an expectation value. That's the corresponding kinetic energy term that we calculated here. And we can ask how this is increasing. So that was the corresponding quantum problem of diffusion. So there's a quantum diffusion problem. You can ask how this is going to grow with time t. In this peculiar case, when tau h bar is 4 pi, you can prove analytically and fairly easily, you can see the notes for some hints, that actually it grows t squared. So it's a ballistic growth, faster than the classical. So it's a very peculiar phenomenon. It's something which is fine-tuned, and it's called a quantum resonance. It's not there in any of the classical. And in fact, it has been proved that not only 4 pi, but any rational multiple of 4 pi has this phenomenon of quantum resonance. But if that's not the case, and tau h bar is some 4 pi times some irrational number, that's the generic case, then what has been observed is that you have, let's say that that's your classical curve, which is going as k squared times t, linear diffusive behavior. Badly drawn plots, don't you know that? Okay. So what happens in the quantum case is that it follows this for some time and then deviates. And then it was a numerical experiment seemed to show that it is much smaller than the classical. And it's now believed that actually it saturates after a long time. So I'll just show you. I need the, yeah. So this is actually from a very early paper. Actually, the first paper on this by these 4 people. And so it's actually a computer calculation from that era. And you see a classical line, which is the straight diffusive line, and the quantum one, which is coming down. And these are the parameter values which are there in that. So this is the phenomenon of dynamical localization, was called dynamical localization, and it's related to localization as was realized later, to localization of the eigenfunctions. We are now evolving in time, but if you were to look at the eigenfunctions in momentum space, they look localized. In fact, localized even exponentially, like wave functions in disordered solids are exponentially localized. And and this was observed also in experiments of cold atoms in 1995. If you look, Raisin's group, they kicked some sodium atoms and saw how the momentum of these atoms are diffusing, and they found a pretty good agreement. And so this is it shows some generic features. One is that quantum and classical will match for some time. and then they will start to deviate, however it deviates. In this case, energy is not being absorbed by the quantum system as much as it's being absorbed by the classical. So there is some break time. And that time, how that time is going with the various parameters are important. We don't have time to go into details of that, but there exists such a break time. Okay, so this is what a quantization of the simplest map, which is not so simple after all, has a lot of interesting physics in it, and continues to be used as a model for many phenomena. So, yeah, please. It's always hard for me to answer a question. So, as I said, the origin of this localization is because of the localization of the eigenstates in the momentum space. Because after all, when you do a time evolution, you can phrase that whole thing in terms of eigenfunctions and eigenvalues. Right? So you have u to the power of n, phi 0, u to the power of n, insert eigenstates, psi j, psi 0, sum over j. So these are phases, e to the I psi j n, and then psi j. So this is your initial momentum states. So, so the delocalization of these states has to do with how these, so in momentum, suppose we were to look at this phi n in some momentum states m. So it depends on how these eigenfunctions are distributed in momentum space, and if they are not very much distributed, if you have some typical eigenstates which are looking like that, it's just a caricature, could be something like that, then it will not be coupling many momentum states. So that's one kind of statement. The other statement is that it indicates that the spectrum is actually discrete rather than continuous. Continuous spectrums can lead to diffusive things. So whether this thing is really a discrete set of numbers or not seems to indicate that as well. Yeah, okay. Yeah, yeah. So I mean that relies on showing that the spectrum is not continuous, and it was shown much later that that's the case in this particular system. But as I said, I mean there are no general proofs. If there is nothing else, we'll move on. So this particular model is kind of an open system, if you wish, or a scattering system. You can have momentum going off to infinity. But we were also talking about Hamiltonian systems, bound energy, area preserving maps, which were bounded on a torus and so on. So these models are not then suited for studying those things. So what is suited in those cases, and I will have time to just mention those things and not go into details of how to arrive at them. But just as in the classical case, we could take the standard map, form the cylinder, identify the momenta, and make it into a torus. We could do the same thing quantum mechanically, rather than studying things on the cylinder. Rather than studying the dynamics on the cylinder, we can study the map. We can study the dynamics on a torus. And the advantage with that is that quantum mechanics is now on a torus, which means that the position and momentum are both periodic. So there was only the position which was periodic, momentum was quantized. Here momentum is also periodic, and position is also quantized. And therefore, you have a discrete set of position and momentum variables. And not only that, it restricts your Hilbert space to be finite dimensional. So that is also so let me just give a very hand-waving thing about that. Suppose that was your phase space, okay? In fact, let's take a unit phase space. You can generalize it to any area if you wish, because we were taking modulo 1 in most of the cases. So that's your QP's phase space. And the area of this is, of course, 1. And let's say that the number of quantum states which are fitting into this is capital N, then 1 over N is so this is is H, because N, that's you can associate, as you know, one quantum state to some area in phase space. You can associate you can associate basically one quantum state to an area H. When area H, you can associate one quantum state, right? I mean, semi-classically, if you were to think of this, you can H, one quantum state. So you can associate with 1 over H quantum states with an area of 1. So N is the number of quantum states which are coming from this. Okay? So otherwise, this looks like a bit odd. It's dimensionless. This is dimensionful. You can put the area here. This is area of phase space, which has the same dimensions as H. So we can deal with an finite dimensional Hilbert space, not infinite. We don't need to truncate. N-dimensional Hilbert space, in which there are states which we will call position states, N, and these are finite. So N is just a number which is going from 0 to N minus 1. And there are corresponding momentum states. I'll put a tilde for a momentum. Momentum values also take. So these are not the eigenvalues of position and momentum. If you wish to define eigenvalues of position and momentum, we shouldn't really, but if we would wish to do that, we could take these as some discretization of 1 over n. So this is like n by n. So as n, small n goes from 0 to capital N, this eigenvalues will go from 0 to 1. And similarly, momentum. So it's a discretization, if you wish, of this phase space. Okay? And this all-important thing is the inner product between these. Not surprisingly, what do you expect this to be? Huh? Sorry? Plane waves? Yeah, but tell me more precisely what. Plane waves of what kind? Yes, plane waves. Yes. Yeah. Huh? What do you call it? There's a name for it. Huh? Well, in the usual QP continuous thing is a Fourier transform. It's a discrete Fourier transform over n sites. 1 over square root of n e to the 2 pi I by n m n. That's the unitary matrix, which is the discrete Fourier transform. So that is the one which is converting states from position to momentum. So this is finite quantum mechanics. It finds its use in many places, and actually it was developed first by Schwinger. He was studying measurements. Okay, as an aside, I mean, the position and momentum operators they're not very nice operators, unbounded and etc. So if you want to study things in a setting where the operators are bounded and nice, so this was Schwinger's approach to that. He said, let's make it all periodic. If we wish, we can let the period go to infinity at the end of the day. So, but it finds its use in many places, from quantum optics and other areas. And in this case, what we can do is, because we are quantizing on a torus, so we have these states, and we can we can therefore write, for example, a standard map on a torus. Okay? I will not write out the, well, the derivation, so to speak, is more or less straightforward. We just have to insert, we just have to do consistent discretizations. Okay? So I'm just going to write out this now unitary matrix in, this is actually position representation. So this is the position representation I had here, is this operator, and it's there in the notes. I'm just writing it, the structure, 2 pi n prime by n, e to the I pi by n, n minus n prime whole square. So now we don't have those issues of discretization, I mean truncation, as I said. This is a n by n finite matrix which is exactly unitary, and this is coming from the potential. So this is the cos q essentially, and this is coming from the kinetic energy. You have this n minus n prime from the fact that it's not diagonal in the momentum. But that's a nice operator. This is the only parameter k, and of course this n. There again, there are two parameters now in this problem, n of or h bar, and n tending towards infinity is the classical limit. So large n limits are classical limits. And then, okay, unfortunately we cannot diagonalize this exactly, it's not surprising. But you can now go to the computer and do diagonalization, time evolution will be exact, and so on. But now the dynamics is entirely on a finite space. So this is somewhat like quantizing an energy Hamiltonian system. There is one more map which we discussed, the Baker's map to some extent. I will write down the quantum equivalent of that, but I will not motivate the derivation of that. There is no Hamiltonian for that, but there is a generating function. So you have to quantize via generating functions. But I write it for the simplicity of this object. The Baker's map, the quantum Baker's map, is again on a torus. So there is this n by n matrix. So it's just a finite n by n matrix. I'm going to write F, I think in the notes I've used G, Fn by 2, 0, 0, Fn by 2. So this is a block, Fn inverse. So it's a block matrix of n by 2 size, and this F is nothing but this Fourier so this is Fn inverse. It's a Fourier transform. It's just a Fourier transform. It is a Fourier transform over n half sites on these two. This is actually giving you the cutting, and classically we cut the Baker's map into two parts, and the square into two parts, and then we stretched one half of it. That stretching one half of it, that this one half is originating from that. So you can very easily generalize this to various other classes of Baker's maps. I did not mention this explicitly. The Baker's map, classical Baker's map, is completely equivalent to a coin toss, is as random as a coin toss. This is a mathematical statement of isomorphism, and it can be quite easily seen as every coin toss is some sequence of heads and tails. To every such sequence, there is a deterministic orbit in the Baker's map, or in fact, just in the Baker's map, or in the 2xn modulo 1 map. It's a one-to-one correspondence. Every deterministic orbit can be mapped to a coin toss, realization of a coin toss. Now you see that when we said periodic orbits are measure 0, you can see that easily in there as well. The fixed point is when you get tails all over all the time when you toss a coin. Obviously, it's never going to happen. Don't risk your life on it. And even this would be a periodic orbit of period 2. Never going to happen. So the fact that they never happened, they are all mapped to periodic orbits of. So in fact, the quantization of this would be the simplest system to study the most random thing. So this was, there are many quantizations after that, but the first one is Balash and Bordeaux, and 1989. But unfortunately, unlike the classical Baker's map, this cannot be exactly solved, except when n is a power of 2, there is some realizations of this. There are some ansatz for this state, for some states in the spectrum. Yeah. Those. Yeah. Oh, it's the correspondences between the symbolic. Yeah. So it's the isomorphism is in the symbolic dynamics. So if you were to split this 0, 1, exactly. But each of these things is really an orbit. I mean, in the sense that we can actually have head to be 0 and tail to be 1. After all, so it's like if you were to run a deterministic orbit, it's going to be a particular initial state is going to be a sequence of left and right, which can be mapped to a. That's actually, these are Bernoulli systems. They are the highest on the hierarchy of classically stochastic systems, as far as deterministic, as far as this class of systems are concerned. So, but unfortunately, it's also not exactly solvable for a finite n. Bit of a. But you see, it's really easy to do the quantum mechanics of such systems, and depends on just how large your n you can do on your computer. So you can test many of the things about random matrices or other things with these kind of operators. So I'm just going to show you what happens if you diagonalize and you get eigenfunctions, and then you look at the eigenfunctions in a coherent state representation such as this QP modulus psi I squared. So we calculate these eigenfunctions, and then yesterday in that I was talking about coherent states which are localized at position Q and momentum P. If we were to look at an eigenstate, which I will call psi I, modulus square, it gives you a window into how the eigenstates look in phase space. Otherwise, we might not have an idea. We might just have some squiggles and wiggles. This is actually for the quantized Baker's map, a sample of eigenfunctions for n is 50. So it's a 50 by 50 matrix, and the horizontal is the position, the vertical is the momentum, and if you see, so these are individual states. So there are some states in which things seem to be more spread out all over phase space. There are some in which it seems to be pretty localized, as here. And in this case, it's a very localized state. And this is also very localized. In fact, when this was first studied by Balash and Bordeaux, they looked at it in position space, and they said that these look like eigenfunctions of a random matrix. And they also looked at, I'll come to random matrices, hopefully. But when it was looked at in phase space, it looked like there was a lot of structure, although it was not particularly understandable. Like, for example, why this state is suddenly after this. And you can see that these are also classical structures. They are stable and unstable manifolds. And this is a scarring. Yesterday I talked about scarring in the billiard by periodic orbits. This is also a scarring by a period 2 orbit. Actually, this is a 1/3, 2/3 orbit. 1/3, 2/3 in momentum goes to 2/3, 1/3 classically. So this is a period 2 orbit that's scarring the state prominently. And then this is also, I guess it's some, I don't know what is the periodic orbit of this, but there's an underlying periodic orbit in this. So many of the states are scarred by periodic orbits. Some of them are scarred by other orbits, not just periodic, other types of classical orbits, and some of them seem to have no correspondence. So this is actually what one is up against when one is trying to analyze a quantum chaotic system. And as n goes to infinity, the question is, what happens to these states in their distribution over phase space? Now, the Berry-Voros hypothesis talked about a Wigner function being equally likely everywhere. So there is an equivalent statement here. You might think about it as if you coarse-grain the states a little bit, this is already in some sense coarse-grained, would it go to some kind of an uniform measure on this? And the limit n going to infinity, what has that got to do with that? Because this is the interpretation of this, is that this is how much overlap this has on this, position. And see, these are like windows into this. These are localized states, which are minimum uncertainty states at this position and momentum. Yeah. Yeah. No, why should it depend on that basis? See, I mean, it is true that if you take some state very arbitrarily close to that, they're not orthogonal states. So, but that's not going to lead to anything, fishy or anything which is, in fact, the Wigner function is also it's a representation in the phase space. So that's not going to really matter. Okay. So this is a completely chaotic system. We also looked at the standard map. How does it look in the standard map? In the case when it is not fully chaotic, because that's why the standard map has a parameter, Baker's map doesn't. So this is a case of a mixed phase space, and you see that there are many. So this actually corresponds to classical islands. If we saw the maps, classical dynamics, so these would actually correspond to islands, regular regions in phase space. These would correspond to some kind of tori objects. So there are things which are scarred by, or rather I shouldn't say scarred, but they are influenced by regular regions of phase space, as well as there are some which look pretty spread out. So here are regular regions, so they don't go into the regular regions. So this is just, again, n equals 50 is just a sample of the things, but a sample of the eigenstates. But there is a belief which goes back to Percival, E.N. Percival, that eigenstates of a quantized chaotic system, not necessarily fully chaotic, suppose it's a mixed phase space, you have some regular and chaotic, eigenfunctions reside either on the regular parts of phase space or on the chaotic parts of phase space, not on both. It's kind of reasonable because we said that they have to be associated with classical invariant sets. Classical invariant sets don't straddle both regular and chaotic regions. They are kind of separate. So eigenfunctions also have this tendency. Of course, this is all statements in the semi-classical limit, h bar tending towards 0. For finite h bar, you will see states, you will see tunneling. There are very interesting quantum effects. In fact, tunneling is affected by the presence of chaos. There is a whole lot of work on chaos-assisted tunneling. It makes the tunneling faster, and so on. We don't go into that. But this is how a mixed phase space discretization will look. You can generate these by just putting this matrix on your computer, taking n equals 50, or you can take n is 1500, and diagonalize it using your favorite diagonalization routine. And you'll get all these eigenfunctions, take some of them. You can either look at them in position space or take some more trouble to construct these coherent states, as indicated also in the notes, and then you can construct these pictures. Questions? Yeah, so this is a more highly delocalized states. So there is some semi-classical understanding of these states, but I will not go into that. But it's not as if we understand we understand a whole lot about them. In fact, we understand fairly less. Okay, so I just wanted to talk about some simple models which you can program almost immediately. And also the fact that there are these nice classical limits of these which are understood completely make them very useful. You don't have to search for periodic orbits and so on. You can just, for the Baker's map, for example, you know exactly where they are. Okay, so 1/3 is over. So now we will talk about eigenvalues, which are really a very important set of information which is there in this quantum system. And so the eigenfunctions are some, you know, they are spread in position space or momentum space, and then we can look at it. What are eigenvalues? Eigenvalues are just a bunch of numbers, real numbers. So that's the ground state, E1, E2, dot, dot, dot. Where is the chaos or otherwise in a bunch of numbers? Yeah, Arna. Oh, no, I'm just having in mind now the usual situation. Hamiltonian, not on the, I'm sorry, I'll be switching back and forth between Floquet and this. But yeah, I mean, if we have a Floquet system, the point is that there are eigenangles on this, and there is no really that something that we can call a ground state, which is smallest. But again, we have some set of eigenangles. Question is, how is chaos or whatever reflected in that? Right. So it's actually nice to vary some parameter in your system and to look at how these energy eigenvalues are changing. So, so this particular thing is from a review by Bruno Eckart, and this is about this quartic oscillator. Okay, we mentioned the quartic oscillator earlier, Q1 to the power 4, Q to the power 4. And this as alpha, so there is nonlinearity here, this is a coupling, and there's also nonlinear. And as this alpha parameter tends towards 0, this oscillator becomes more and more chaotic. And as alpha is exactly 0 and gamma is not 0, it's a very interesting system. It's a pure x square, y square potential. And for some time, people thought it was fully chaotic till people found some very irregular regions in that. You see, it's a homogeneous system, so it's independent of energy, the structures in the system. And also, it's an open system. That is, when alpha is 0, it's an open system because at any energy, you can have free motion along one of the, if Q1 is 0, it just goes along Q2. So, so it's an open system, but its quantum mechanics is a discrete spectrum. That has, again, been proved. But anyway, we're not going to set this to be 0, but the point is that as alpha is decreasing, it becomes more chaotic. That's all we need to keep in mind. Oops. I don't know why this happens. I guess that's because I switch between this and that. Yeah. So what you're seeing is this alpha parameter here, gamma is 3 is fixed. And if alpha is large, in fact, if alpha is 1, it's integrable. You can prove that. You should probably prove that. It's in, it says that alpha. Yeah. Okay, anyway. So there are 48 eigenvalues of this quantized Hamiltonian. So this is actually also an infinite dimensional system. So you need to truncate it. You have to use some basis, truncate it, convert some energy. So it's only 48. So it's the lowest 48. It's an early paper. And so these are regular. And as this alpha is decreased, it goes into chaos and classical chaos. And this is what happens to the energy level. So here is a window of these energy levels, which is shown here. So what difference between this regular region and this chaotic region is that in the regular region, you can see a lot of crossings of energy levels. Whereas in the, when it's classically chaotic, you see avoided crossings. They don't like to be near each other. They avoid each other. There's actually a bunch of avoided crossings. So in fact, this is an important signature of non-integrability or chaos. And that's seen, another example is in a circular billiard, you put a magnetic field. So if the magnetic field is, so it's this kind of a Landau diamagnetism problem. And you observe the dynamics on this. So if the billiard is already circular and you put a magnetic field, then it remains integrable. And as you're changing the magnetic field, the energy levels are being plotted. You see a whole host of crossings. They don't care about other levels. They just cross each other without anything. Here, the same thing, but with an elliptic billiard. Elliptic billiard, remember, is integrable. But when you put a magnetic field, a homogeneous magnetic field, it does not remain integrable because, as you know, the orbits, what are they called? Cyclotron orbits, their symmetry conflicts with the symmetry of the ellipse. They're not circular anymore. And then you can have chaos. And you can see, again, the same kind of energies, you see a whole host of avoided crossings. So that's how a irregular or chaotic spectrum will look. That's how a regular spectrum will look. Okay, so there are many, many examples of this. And this has some effect, for I just mentioned diamagnetism. So this has some effect on how the susceptibility behaves as a function of the magnetic field in these things. So the susceptibility is a function of the magnetic field. This is the circular billiard, it decreases. This is the elliptic billiard. Actually, at b equal to 0, it increases with these violent behavior here, which I believe are because when the Fermi energy crosses, undergoes one of these avoided crossings. So these are actually signatures of that. Okay, so there are physical effects of this thing. This is yet another example of a hydrogen atom in a magnetic field. The spectrum of hydrogen atoms in magnetic fields, as I said, hydrogen atom also in a magnetic field due to clash of, number of degrees of integrability is lost, can undergo chaos, and for large enough magnetic fields, you will see avoided crossings in that. Okay, so this is a very general phenomenon. And you will also find this in the quantum maps, which I said, I don't have a picture of that, but if you were to vary as a function of this standard map, for example, standard map parameter k, the eigens, the quasi-energies or these eigenangles, you will again find a very similar phenomenology that when k is small, they will cross, and when k is large, there will be avoided crossings. Okay, so how do we study these? How do we formulate this? So for that, I need to, so where is the chaos in this, right? The fluctuations. So let's just look at these eigenvalues. Now you don't worry about the circle. Look at just the some bound spectrum, some discrete bound spectrum. We have these energies, and we have, let's say that we plot the following, the staircase function as a function of energy. What is the staircase function? Is simply the number of levels less than a given energy. Okay, so if there is a ground state here at E1, there is nothing before that, and after the ground state, there's one level. Until the next level, there's nothing, there's only one, and then there is two, and so on. So you draw the staircase. And here, the staircase is drawn for a quartic oscillator. For the potential is simply x squared, y squared. Okay? And what you see is that the staircase is here. There is an exact staircase. So it has a kind of an secular or average growth. It has an average growth, and actually we're not interested in that average growth. And that average growth we'll have to remove. So this is average growth, which we will denote in n bar of E. So we'll write n of E to be n bar of E plus some oscillatory part. Okay, so that's the exact staircase. This is the average staircase, which is the average curve, which is a secularly increasing or whatever curve plus. So how do we find this average? So this is actually the standard density of states problem which you would study in statistical mechanics or maybe quantum mechanics. How do you find the average density of states given a Hamiltonian? What is the dispersion relation? Sorry? Maybe we'll start with this. You can go through that, but we can argue in a different way. But let's just do it simply in a semi-classical way. Okay, and that's good enough for this. So we said that we will associate with a H one quantum state. Okay, and in d dimensions is H to the d. I'm sorry, in d degrees of freedom, it's H to the d. Okay, so with a volume H to the d in phase space, we associate one quantum state. For energy, classical energy is E. This defines this energy shell, H QP equals E. There is a volume underneath that, which is just given by this Heaviside theta function, this integral. Right? So if H is smaller than E, it is 1, otherwise it is 0. So we integrate this over all possible phase space, gives you the volume underneath this energy shell, and we divide this by H to the d, that gives you the number of states less than E. It's a semi-classical formula, but actually you can do a more, you can find corrections to it. It's called the Weyl series, and but this is the most important part of the series. Okay? So for especially high energies, this is a good function, good thing. So you should be able to calculate the smooth. So this will give you this approximation to the staircase, a good enough approximation. So for example, for the quartic oscillator that we saw earlier, you should be able to calculate this density of states. I show you essentially that it's better to take a density of states rather than this. The density of states is related to n. So let's write out n of E. N of E is this theta E minus Ej sum over J. Theta again Heaviside theta function. So this is the exact definition. That's the staircase function. So it's counting, it's putting 1 each time Ej is less than E. And the density of states is just the derivative of that. And that's the sum of the delta functions. So if you want to find the energies, you have to find the density of states. So this one has a split into a smooth part and an oscillatory part. We can just take a derivative of this. That gives you density of states. There's a similar split into an average density of states and an oscillating density of states. Actually, all the information about exactly where the states are is there in the oscillating thing. This is just some background. But that's all that is usually used in statistical physics, and that's needed. So the route to finding that might be to look at the density of states, and you can basically look at the partition function and do a Laplace transform to get this kind of thing. But you can, it's just a trick. You can do the integral in other ways. Okay, so once we find this average, we subtract it. We are not interested in it. we are actually interested in the oscillating part. And so we look at how the oscillating part looks. So for example, in the oscillator case, this smooth thing goes as some e to the power 3/2. Okay? And in the case of a billiard, it just goes as E. You should already know that the density of states is constant for a billiard or a particle, what they call quantum dots. Okay, so we are not interested in this growth itself. We are interested in fluctuations. This is what one means by fluctuations, that we have subtracted it and we are looking at these fluctuations. And now you look at the fluctuations in two cases. One corresponding to an integrable system. It's the same oscillator, but this is an integrable and that's chaotic. And it's a function of the energy E, and that's the oscillating part. So first of all, visually you can see that there's much more oscillations. The strength of the oscillations is much more in the integrable case, the regular case. There's much more oscillations. The amplitude of these oscillations is contained. Other thing is actually if you go up in energy, these oscillation amplitudes will increase if it's an integrable system. But it is contained essentially between ±1 if it's a non-integrable chaotic system. So there's vast amount of differences in the fluctuations, and the fluctuations is what contain all the information about where exactly the energies are. So a study of these kind of things, actually people have even looked at this as a time series and done some time series analysis kind of thing. So you can throw a lot of, you could probably think of this as stock market fluctuation, something like that. And then you can do a whole lot of statistical analysis can be thrown into this, but it seems to tell us that we need to do some statistical analysis. But how do we do the statistical analysis? We have these vastly different systems, including actually the Riemann zeta if you want to throw it into the hat, into the ring. So they are vastly different things. We need to put them all into one framework. There is this very useful thing called unfolding, which was done by, I think, nuclear physicists and carried out here, is simply this. We know this average density of states. It's some smooth function of energy. We take the actual energy levels, the actual EJ, and it's a monotonic function. So actual EJ, and we get a new set of numbers xj. All the information about EJ is there in this. It's just a mapping. It's just a function of this to this. So rather than studying EJ, one studies these xj. These are called unfolded spectrum. It's unfolded because now if you looked at at xj, you will find that, and you should think about why that is, that it's actually fluctuating about the line, 45-degree line. And the mean spacing between these xj will be automatically 1. So you should think about why the mean spacing of the xj is. So what I mean by that is you look at nearby things and you look at some mean spacing, this is already 1. Or it's very close to 1. Actually, the average will be equal to 1. Okay. I think it's the end of the thing. So that's called unfolding, and so we need to do this for every spectrum that we have. And for spectra on the circle, like the unitary operators, it's actually easy because if you looked at how the corresponding thing is for the eigenangles, how the eigenangles are distributed, in most of the cases, I can't assure you that it's there for all the cases, but in most of the cases, it is true if suppose there is really an, if you have some, well, let me just say that in most of the cases, the density of states is uniform on the circle already. And so the spacing between them, if there are n of them, is just 2 pi by n. So to make some angles into a unit spacing, we just have to multiply it by n by 2 pi. And the billiard is also a similar thing. You don't have to do anything to unfold them. But every other spectrum you need to unfold. Okay, so now we will analyze statistics of these xn, these unfolded levels. We will see that actually they are very close to that of random matrices, has been studied in random matrix theory, which was my third part. But I shall stop now. And but it's quite amazing that, there's nothing random about this matrix. Fourier transform, inverse, discrete Fourier transform, 0, 0, Fourier transform. Or about that standard map which I wrote. There's nothing random about it. It's a combination of these things. Yet, it has these kind of statistical fluctuations of these eigenvalues are that of random matrices. There are deviations because of the dynamics in it. But for a large part, it is described by those of random matrices, and there's some universality in these spectra. Okay, so quick questions. We meet tomorrow. Thanks. Actually, we meet again this evening for the tutorial, I guess. Okay.